Hi, and welcome to the lab. Today we're going to take a look at a measurement that I was making based on a request, or I should say some feedback I got from the EEV blog IRC channel. I was working on a project. I asked a question about something and I got another question in return. So let's go take a look at the actual project that I'm working on, at least a little bit of it, and look at see what we're actually interested in measuring. What's the precise measurement and the phenomena that we're looking for, and then let's see if we can set that up on the bench and go ahead and measure that value and see what we get. Alright, so let's take a quick look at this circuit in a bit more detail. I'm not going to go over the whole thing, but I just wanted to give you an idea of where the particular problem area that we're going to take a look at and do some measurements actually is. So what we've got going on here is a Arduino. Well, in fact, actually, this is not an Arduino. Okay, this is completely 100% nothing to do with Arduino whatsoever. It just happens to have the same functionality, and it has Duino in the name. But other than that, it is completely unlike anything else. So this is one that I designed, quote unquote, designed, put together, and assembled, and it has an Atmega 644 in it, so a bit beefier version of the one that's used in official Arduinos. So this guy's generating a PWM signal out of one of the data pins here, and that's being fed through into a opto isolator for other reasons, which I'll get into in a different video, not this one. And that's getting then pushed, or controlling, I should say, a MOSFET, an NFET, which is basically generating a PWM pulse using a reference. Right now it's just a crappy reference, but the reference voltage is 6.2 volts for reasons that will become apparent later on when I do a video on this actual project. So that PWM signal now gets filtered through an RC filter here, and then gets fed into an op amp right here, which will then do some magic. In fact, it's actually a voltage controlled resistor here with this op amp, a few of these resistors, and another FET over here. But on to our problem. When I was asking a little bit about this, because one of the problems with this particular design is that this FET is essentially opening and closing. I should say, when it closes, or not closes, I should say, when the gate goes high here, it basically conducts straight to ground. So it's essentially dumping from the other op amp on here. The 6.2 volt reference is buffered in the op amp, and then it's basically passed through a 10K resistor right here to the drain on this NFET. And of course, when when you have a high signal on the ground, you're going to end up getting a path directly shorted to ground. So of course you're dropping, well, not a huge amount of current, but enough, a few milliamps or a couple milliamps to this 10K resistor to ground every time the pulse goes low in the PWM cycle. So that's not fantastic. And I said, well, I asked, is that a problem? And the first thing I got back was, well, okay, that might not be a problem, yes or no. There's better ways of doing it, and I got a few suggestions which I might go into. But the big thing was, well, that PWM pulse frequency, does that leak through my RC filter into my my op amp here, which was being used to set this voltage controlled resistor? Because if it is, that means my resistance here is jiggling by ever so a small amount. Essentially, I'm getting noise in here because of noise coming through from that PWM signal, not fully being filtered. I said, that's a good question. I don't know. When I tested this, it seemed to be relatively clean. I was getting a fairly clean voltage, and granted, okay, define clean. I wasn't looking for tens of millivolts. That was too much. It needs to be in the realm of a couple of millivolts, 2, 3, 4, 5 millivolts. That's not a fantastic or high precision filtered voltage in this case, or a reference, but it's good enough for my purposes here, because there are other reasons why it's not going to be that big a deal. But I figured it was going to be a lot less than that, actually. So, I figured it'd be maybe a millivolt, maybe a bit less. But then again, I don't think I'd done the full test on it, or at least measured it. So that's what we're going to go do now. So we're going to go ahead and we're going to set up, and I'll show you how that's what the setup will look like. But we're going to go measure the noise on the output of this RC filter. And at the same time, we're going to scope the actual signal coming in from the actual gate controllable PWM signal. so we can see whether or not there is some correlation, if there any noise that's happening when that PWM goes on. So stick around, and I'm going to set that up, and we'll be right back. Forgot one thing, mostly just for completeness sake, because again, I'm going to go through this in a later video, or a video later on. But the actual VCR, the voltage controlled resistor, is actually coming through back here and to the back of this power supply. And the whole point of this power supply is that, or the interesting part about using this power supply is that we can control the voltage that's on the output remotely. And this was originally intended, I would imagine, for controlling via, say, a remote variable resistor potentiometer that might be in a different room or a different bench or whatnot, or maybe even, you know, mechanically controlled, because these power supplies are fairly old. So I wouldn't have thought that these would be electronically controlled. And of course, the resistance is really easy, right? You can just, you know, program it with an arbitrary resistance. Say, for example, if you need a very particular voltage, you don't want to dick around with the knob in the front. You can just, you know, whack a resistor in here and boom, you're done. And the voltage is controlled by adjusting the resistance from I forget exactly, it's not zero ohms, it's like because the 0 ohm resistor means a dead short here. Actually, sorry, it could be 0, pardon me. So it's from 0 ohms up to, I think, like 1,100 ohms or 6,000 ohms or whatever, 6K. And it was some number, I forget exactly what it was. I think it's 1,000 ohms. And but of course, the idea of course is there's always some current being flowing through here, which allows you to get a regulation. It uses that internally to regulate the output voltage. So of course, you want to have a very, very, very clean, or I should say, as clean as possible resistor here, because that allows you to have consequently a clean output, no noise and whatnot. The other thing of interest here to note is that this should never be open. So you can find these power supplies. These are Power Design Incorporated. This one particular one is a Power Design Incorporated 650A. You may have seen in a few of my other videos, I have a couple of other ones. I have a 650C and 650D. I love these supplies. They're fantastic. They're 0 to 60 volts, 1 to 5 amps, depending on the voltage range you're at, but they're linear in some cases. In this case, you have two ranges. You have a 0 to 6 volt and a 0 to 60 volt. And current limiting, the whole balls. It's fantastic. But a lot of times you'll find these guys with, say, either a blown fuse, and there's an external fuse here for the input, the mains input, but there's also an internal fuse, which is fusing the secondary side of the linear transformer in here, because these are linear supplies. And one thing you'll find is that'll blow if, for example, the tie strapping here, which is, like you can see here, it might be a bit difficult. I'll zoom in a little bit. But I don't know if you can see that. Might be a bit hard. Let me just go and move. Right here you can see that. So there's an actual strapping that ties these pins to, you know, the sets of these pins together. And normally you're on this voltage controlled resistance or remote programming set of terminals, you'll have the same thing. Although if you find one of these supplies on eBay marked as not working, and you see the current limiting light coming on and blinking, that's a pretty darn good sign that this sucker here, this strapping on this particular set of remote programming terminals is missing. And if it goes open circuit, it will basically jam the output voltage to a maximum amount, which will usually trip the over voltage protection crowbar that's in here, and basically make it as if the power supply outputs 0 volts and is completely inoperative. But it's perfectly fine. You just replace this with anything. I've used a piece of wire. I have one right here. You can see. Let's get that in focus. So all it is just a quick little tie strapping that would then go over here and tie that together, and perfectly working as brand new. Of course, doing a bit of cleanup. So excellent supplies. Keep an eye out for these guys. Keep an eye out to see if the strapping in the back is missing. Usually they'll show a rear photo, and you'll see right away if it's missing. And if you see a fault where the light, either the fault light or if the current limiting light is flashing, that's typically what it is. So let's get back on to setting up that measurement and taking a couple of measurements. All right, so where are we and what's going on here? There's a bunch of things, so I'm going to walk you through it. Bear with me. So we have our Arduino here. Our fake Duino, our 644 Duino, plugged into our circuit here. It's going to generate the PWM, as I said. We have power coming in on two of these. So we've got power for the micro, or the 644 Arduino coming here from this power supply. So this is going to provide the power supply. And as I said, I set up these isolated for other reasons, so I do need 2 power supplies, and I'm going to power them from 2 power supplies just to keep everything sort of the same as it would be in circuit. So this is the guy generating our PWM signal. We have our circuit here powered by another power supply, the HP up there. That's going to run 12 volts. The 644 Arduino is going to also be powered by 12 volts from this guy. The output of this is going to control this power supply here. So this is going to be remotely controlled by that voltage controlled resistor I had said over there with the MOSFET, or done by the MOSFET and the op amp. The output of that is going to go to a electronic load over there, and it is also, we're going to pick off the output right here via a probe using a BNC to probe tip adapter. This probe's in 10x for the moment, and that's going to go up to our oscilloscope right here, which we're going to see the output and look for any noise there. Now I'll set up, I don't have the actual other probe, I'm going to set that up before we do the test. That will plug into the PWM, and in this particular case, just to let you know, so these 2 are isolated, and I might go and I don't know yet. Well, you know what? Screw it. I'll go ahead and I'll monitor on this side. But just to let you know, this circuit here doing the voltage controlled resistance is tied galvanically to the same reference, ground reference in this case, as the power supply through the back through the back connector. So keep that in mind. So when I'm scoping with my scope, I'm not going to have 2 different ground references. I'm going to use the same ground reference. So right now, the scope is referenced to ground through the external connector, and you can see it right here. I'll just go ahead and undo this. You'll see the external shielding on the probe right here. Okay, so that's going to come in through the BNC connector, which here I'll see right here. So it's going to come in through the BNC connector, and it'll pick it off from the ground, or the ground reference of the negative terminal here, which will be the same at the same reference level as the circuit here doing the control, not the Arduino, the circuit doing the control. So we'll just go ahead and put this all back together. Whoops, clumsily, of course, because it's the way I roll. We'll get the other probe out, hook that up so we can monitor the PWM, start the circuit up, and we'll try and take a measurement. All right, one other quick little thing, just in case it wasn't obvious or clear. You may notice that this probe has no ground connection anywhere, right? Where's that darn ground connection? Well, again, it's because this circuit here, along with, I'm going to zoom out, whoopsies, wrong way, along with this ground here, which is where our other probe is connected, it's the same ground reference, all right? So it's safe to do this, and just to let you know. This guy's still shielded, no worries there. We're not going to introduce any noise here. Not that it would make a big difference anyway, because this is a huge 12 volt PWM signal and would squash any noise anyway. So let's get on with the test. So I'm going to go ahead and turn. Should I zoom this out a little bit? Okay, there we go. So I'm going to go turn the micro on now. So now the micro is generating a PWM pulse coming through here. We're going to go and turn on the actual circuit here. And we'll go take a look at the scope screen and take a quick look and see what's going on here. All right, frame that up a little better. Alrighty, so we have the 2 traces here. You can see the top trace is our where we're probing at the output of the power supply, and the bottom trace is our PWM signal. This is the one on the isolated quote-unquote side of that circuit. So this is where this is coming right out of that MOSFET, and of course when that FET's on, the signal is grounded, and when the FET's off, the signal is high, or at 12 volts and something. And we'll just go add a quick measurement in here, and we'll do a let's say V-top measurement. Bingo, there we go. Sorry, not 12 volts, 6 volts, right? Because our reference is supposed to be 6.2 volts, and again, like I said, the reference on this is pretty crappy, and I'm not paying attention to too much because I'm just curious about getting a couple of the other properties of the circuit and not specifically the accuracy of the circuit. And in this case, oops, there we go. So of course, we have a turn off here. So the duty cycle here should be set to 10%, if I remember correctly, or something of that nature. I don't remember exactly, but it's something along the lines of that. So what we should see on the output is something close to 10% of full scale, which in this case full scale would be 6.4 volts. So it should be about 640, give or take, millivolts. I should say the output PWM. But we're not going to look at that. What we're going to do is we're going to go over to channel 1 here, pardon me, and we're AC coupled there. We're DC coupled on channel 2 and AC coupled on channel 1. And what we're going to do is we're going to turn on the bandwidth limiting, because we're interested in something that's fairly low frequency. So the PWM frequency here is, actually, let's go and measure that. Frequency, there we go, 4.9 kilohertz. So I'd set to 4.8, but it's close enough, as makes no difference. So for channel 1, we're going to set the bandwidth limit on, because we're not interested in noise that's been added due to high frequency. We're interested in noise that's specifically due to the PWM signal leaking through our RC filter. We're using a 10x probe, so we're going to set our ratio to 10x. Again, 1 meg input, because we're not worried about passing any signal through the probe. It's not a 50 ohm measurement or anything like that. It's really, we're just probing that circuit, and we want to load it as little as possible. So given that, I think we're ready to give this a try. So now I'm going to turn the power supply that is being controlled on, and we will now see if there's any measurement here. And of course now we're at 200 millivolts per division, so if we see anything right now, this is horrifying. This is really, really bad. There's a huge amount of noise being leaked. I would be very surprised, and you might see, I'll turn this on to 20 millivolt per division, and you can potentially see right now there's some garbage going on, and I'm going to just pause this for a second. I don't know if you can see that. Try and turn that up all the way, make that really obvious. So this stuff here, all right, I'll start the scope running again so you can see it. Oh, that's horrifying, right? Well, that's because I have really bad LED lights that barf huge amounts of PWM signal into my environment. So when I'm taking measurements, and of course I've got another one down here, but I don't think that this little stuff here, I'm not sure where that's coming from. That's coming from some other part of the test setup. We'll ignore that for the moment. But you can see that, of course, I turn these lights back on, and we're gonna get a huge amount of noise. Boom! Look at that. That's crazy. So we'll ignore this for the moment. But when it matters, I'll turn off these the overhead lights so we can get as clean a measurement as possible with the setup. But for the moment, we'll ignore it. And again, that's if we're looking at this. This is 500 and some odd kilohertz or something. If we go ahead and trigger on channel 1. Sorry, 40-something kilohertz, 30 or 40 kilohertz. So, it's above our PWM frequency that we have in our circuit, so we should be able to ignore it. Anything at that, let's say anything at 20 kilohertz or above, we can ignore that for the moment as being not directly a result of our PWM signal leaking through. So let's go ahead and change that back to channel 2 we're triggering on. So now we're triggering on just the PWM signal. All right, let's give it a try. So I'm going to turn the output on, and I'm at 20 millivolts per division. I'm going to set that to 5 millivolts per division, and I'm going to turn off the lights to clean up that signal a little bit. And maybe we should go and do a couple other things first. First of all, we're on normal acquisition here, so not the high res mode. We're in the regular acquisition. It's selecting the sample rate and memory depth automatically. Right now it's setting the memory depth to 1.4 megpoints, which is fine for the moment. Anti-aliasing's turned on. Could potentially turn that off, but that's all right. Inside our triggering menu, we're set to DC coupling right now because we're coupled on this guy. And that's the trigger, of course, right? The channel 2 is also DC coupled, but channel 1 is AC coupled. So keep that in mind. We're only looking at the top of the wave I should say we're not looking at the waveform full scale on channel 1. We're just looking at the wave itself and not the full scale, say 12 volts or whatever that's going to be output from your or whatnot. Our noise reject is turned off because right now I would reject normally the 4 kilohertz signal if that was the case. So let's go and clear all that. I'm going to turn on this power supply and let's see what happens. Woohoo! All right, there we go. Okay, so now it's going to see it jumped all the way up because the cap is charged. Now we're just going to get what's on the ripple that's on there. So that, that doesn't look too bad, right? I mean, that's not horrible if we look at that. So let's take a peak-to-peak measurement right now. We're measuring about 14 millivolts peak-to-peak. That's still pretty high. I'm going to turn that off and let that settle again, and we'll see what else we have there. And you'll notice at peak-to-peak, it's still measuring about 14 millivolts. So I am already skeptical. At this point, I was already skeptical that this is showing us what's really happening, because it looks like there's a noise floor that's too high to show what's actually going on in the measurement. So we did a couple of things, and we'll go through and actually look at a couple of the things in this setup, and let's see if we can try and identify the sources of problem.